Okay, so sorry about the abrupt stop last time. I set a timer and then it paused, so and the video just automatically end. So, okay. Yeah. So I'm not sure when but okay. All right. So yeah. So this time let's continue with our proof. So last time I think we stopped at the past homotopy lifting property, right? So let me just maybe state what I maybe paused, but maybe I paused last time. So let's see. So where am I? So yeah. So okay, last time we stated the past homotopy lifting property. And let's see, so I won't state the statement. So yeah, so I think we stop at where I define a map H hat from this AB cross 0, 1 to this X hat by the map T as go to H hat as T. Okay, so this is the lift. And we get, so we get that the H hat, the lift at A is the same as the x0 hat, okay. And then, okay, so that's it. So, so maybe, so this H, remember it has a lift, and defined by H of ST is equal to this HST. So this is the definition of this H. And then this H, oh, sorry. I think you actually add like a hat because it's like a bit. And then, oh. Okay, I think in the books they are, okay, sorry. I forgot to mention, okay, so I'll bring to do, yeah, so the author of the book actually, yeah, okay, I'll bring the book next time, okay, I'll bring the material that I used next time, okay. So, yeah, so the author actually, okay, so never mind. So, thus, okay, so and, yeah, I want to say that the author actually agreed with, like, yeah, so, okay, so, yeah, and we get this H hat, A is equal to X naught, okay, and then we'll have this, okay, we have this gamma composed H is equal, H hat is equal to H. Okay. Yeah. Alright, so, okay, so now, if the set, okay, so if the set A, which is in this A, B, cross 0, 1, okay, to weight of of points of discontinuity for H. For H hat, sorry, is non-empty. then we may set the C, which is defined to be the inf taken over the set of all T in A B, close interval A B, such that this T cross interval 0, 1, let me just do here, intersect A is not empty. So C is being defined to be the infimum of this set. Okay. So now, let's see. Okay, so now what happened? And okay. And we may choose this R in the closed interval 0, 1 with C, R is in a closure. Okay, so why we can choose this R? Let's see. Okay, so C is like the infimum, okay, of this AB such that this T, okay. Okay, so basically, so A is a subset of this AB cross 0, 1, right? So you can think of, okay, so you can think of this as, so here I have my AB here, and then I have my 0, 1. So remember that they are closed intervals, so they form a closed rectangle, right? So this is the set. And then A is a subset, okay. And then, okay, and then, so we set C to be the infimum of the set of all T in AB, where T cross, okay, so infimum of all T in AB such that, okay, so, yeah, so T equals 0, 1 inside A is not empty. So T equals 0, 1, okay, so T is in, okay, so each T, okay, so infimum of T, okay. So if you have a T in AB, then the thing is that if you cross it with 0, 1, right? So it may or may not intersect A, okay, but here it says A is not empty, so not empty means that there must be an element inside this, all this A, right? Yeah, so this element, I think there must at least like a T, right? Because this element, it has a, yeah, it has a coordinate, right? It has a coordinate. Then I just take T to be whatever the, because the first coordinate is in AB, right? So because then I just take T to be whatever the first coordinate. So this set is not definitely not, if A is not empty, then this set is not empty, okay. So now what happened is, so I take C to be the infimum of this set, okay. Yeah, so this set is bounded, right? So therefore it has infimum. All right. So okay, so let me see, and then we may choose R, okay, with oh, I see. Okay. So yeah. Because you see, this C must lies in this interval AB, right? Because you see that this T, these are all, yeah. So yeah, these C are they are the limit point of. There must be a sequence that converges to this C, right? Okay, and then you see that because the set is AB is like a compact set, right? By the corresponding compact by the So therefore, it contains all the limit points. So this C must be contained in this AB. So since C is contained in this AB, then so Y is contained in the A closure. Let's see. Y is contained in C closure. Okay, so because since it's the infimum, then okay. But why? Let's see. So basically, why? So basically, the idea is that this C is the infimum, right? So you can take a limit of T that this T converges to this C, right? Yeah. And then for since for each T there is like a small little point, right? Within the T. So and then since the distance of T to this C is can be even very small, but the thing is, what about the other point, right? So if the other point just bounce through the upside down, so what will happen? So does it even converge or something? Okay, I see. So the thing is that here this 0, 1 interval is like a compact set, right? So basically imagine that for each of these T, I can pick like the corresponding like R, which kind of depends on the T, right? So basically imagine that you have a sequence, right? You have a sequence Tj, right? You have a sequence Tj that approach to this C, right? Where j equal to 1 to infinity. Okay. So you pick that sequence. And for each Tj, so imagine that just imagine that this is the C, right? And then you can pick this T approach to this C. You can pick this T like closer and closer approach to this C. And then for each limit point, for each point Tj, right? Because this T intersect this A is not empty, right? So imagine there's maybe some A here. I can pick a point within I can pick a point within this interval, right? So let's say that the point we pick. So for Tj, right? Maybe we pick like say Rj, okay? Because in fact analogy we can pick a point, okay? So now, okay. So here you get another sequence, Rj. J equal to 1 to infinity. Okay. So now because you see that the interval like 0, 1 is a compact interval, so there is like a subsequence that this one converges and the limit is exactly so we can let the limit to be this R. Okay. Okay. So that's the argument here. And then okay. So okay. So next, if epsilon equal 0 is sufficiently small and this E which is C C minus epsilon, C plus epsilon intersect A, B, cross these R minus epsilon, R plus epsilon intersect 0, 1. Okay. Then we tell that this H of this D is contained in some evenly covered open set U. Okay, so let's see why this is true. So here we take D to be defined to be, okay, this C, remember C is like the infimum, infimum, right? And then this D is being defined to be C minus epsilon, comma C plus epsilon intersect AB. Okay. Okay. So and then cross this. Okay, cross this R. If epsilon bigger. Okay, sorry. Yeah, if epsilon bigger than 0 is sufficiently small, and then this D being defined as the and then D, which is that. Okay, then okay, so basically Y, we can pick this epsilon. Okay, so that this HD is contained in some evenly covered open set U. Let's see. So I know that this, okay. I think the argument goes like, because you know this C comma R is in a closure. Oh, sorry. Yeah, this C comma R. Okay. So here, so suppose that we have an infimum, right? So we have infimum. Let's say maybe I just point it as here. Okay. So let's say that this R may be here. It converges. Okay, this is the point C comma R. Okay, so right here. And then I pick an epsilon neighborhood of this point. Okay, so okay, let's see why HD is contained in some evenly covered open set U. So basically, if you HD, okay. Okay, I see. So because, okay, so here we are just talking about H, right? Not H tilde. So we know that this H is a homotopy. Therefore, it is continuous. Okay, so here this H wrap this domain into like some variation, like hang on a second. Okay, maybe let's just focus on the given point at this CR. Okay, so suppose that you have this point as this H at C comma R. Okay, so this is the point H of C comma R. So HD is contained in some evenly covered over say U. Okay. So why HT is contained open? Okay, I see. So basically the idea is that, remember for each point in the covering space, you can pick a neighborhood that is evenly covered by the covering map. Okay. So here this is the point, and then we pick a neighborhood that is evenly covered. Okay. So now what happens? So now if I take the inverse image of this set, because H is continuous, so therefore we can take the inverse image, then this set must be open in this AB cross 0, 1, right? So it's like open. Since it is open, then yeah, I think we are good. Yeah. So if it's open, then I think the case is that if it is open, then it is open in the topology, right? So basically, this topology, I think, is given by the subspace topology, right? So if you take the subspace topology, then it is open, means that it is some open set intersect this AB cross 0, 1, where the open set in Rn is open. So, sorry, in R2. So, and then that open set, you can pick yeah, so basically for that open set in R2, because you can pick a ball, right? And then you can pick the square, and then the square intersect that sits inside this open set. Okay, so yeah, sorry, roughly speaking, that's the idea. Okay, roughly speaking, that's the idea. Okay, so let me see. All right, yeah. All right. So now what happened? So now, okay. So now, shall I erase it? No, I'm not sure. Maybe just bear me a little. Maybe let's just continue. So, okay. So if C equal to A, then we have that this R maps a neighborhood where am I? A neighborhood U naught of this X naught hat homomorphically onto U. Okay, so let's see why it's true. So if C equal to A, okay. So what happens if C equal to A? So C, remember, C is like the ephemeral, right? So if the ephemeral it hits the lower bound A, right? Then R maps a neighborhood of U naught of then R maps a neighborhood U naught of X naught hat. Okay, so why R, okay, what is U naught? Okay, so what is X naught? Oh, okay, okay. Okay, what is R? Okay, neighborhood U naught of X naught hat homomorphically onto U. Okay, remember that this U is like this set here, right? So I think what I wrote should be gamma instead of R. Okay. Remember, this gamma is like the covering space map. Okay. So, okay, that makes sense. So, okay, yeah. So if this C is equal to A, then this point is like the, I think that's the only point, right? Yeah, so whatever, right? Because, yeah, if C, yeah. So by this argument, if C equal to A, then, wait. Yeah, sorry, I think yeah, so previously the homotopy, it has the property that this H of, sorry, yeah, so H of A of anything is equal to this X naught. So, so then, okay, so yeah, so if this is equal to A, then this is X naught. Okay. So wait, why this is mapped to a neighborhood U naught of X naught hat? Oh, okay, because yeah, because this gamma is evenly covered, right? So that's not yeah, because this X naught is one of the pre-image of this X, right? Okay, yeah. Is there any issue here? What's the neighborhood you know of X? Okay. I think that's by the definition of covering space map. Okay. All right. So let's continue. So, okay. What's next? Um, and we get a continuous lifting a gamma should be the capital gamma restricted on U naught inverse composed with this H restricted on this D from C to U naught. That is equal to X naught hat along this A cross this R minus epsilon comma R plus epsilon intersect 0, 1. Okay. So let's see why it's true. Okay. So we get a continuous lifting. Okay. Okay. So this is the gamma restricted on the U naught, right? Okay. So remember that this gamma restricted on U naught is like a homomorphism, right? It's a homomorphism. Okay. The inverse. Okay. Take the inverse. Okay. Composed with this H restricted on D. Okay. So remember this D is like this cover we just defined, right? And then this H, what is this H restricted on D? So this H restricted on D is what? Yeah, just the H restricted on D, right? Okay. So H restricted on this D to U naught. Okay. Okay, because this gamma is a homomorphism, so we take the inverse. And then so we get a lifting. So why is a lifting? So because both H and this gamma which is on U are continuous, right? And then if you take the composition, wait, what do you mean? That is equal to x naught. Okay. That is equal to x naught hat along this A cross. Okay. So I think what means what it shows here is that because so this is definitely continuous map. Okay, because H is continuous, this is continuous. And then why is lifting? Because if you take the so if you take the projection, then it just give you, if you wait. Okay. So I think there should be a lifting of this H restricted on D, right? So basically, if you take the covering space projection of this one, it should, if you take the covering space projection, then it should give you back Y, it should give you back H. If you take the, wait, what, why am I confused? So, it's definitely a projection, right? So it's definitely a lifting, right? Because, okay. That is equal to this x naught hat along A, that is equal to x naught hat along A, okay. So what is x naught hat? So this x naught hat is like the width of this map, right? And then along this A cross, what is A? A is that. A is the point, okay. A is the point. And then A cross that. Oh. So remember that this, so this is just that. This R minus, so this R minus epsilon R plus 1 is like 0, 1. It is just the what you call it? This is like the path parameter, and then this is like the variation parameter. So these are like the variation parameter, and then that is equal to x naught along a. Okay, so yeah, I think it's true, right? Because this so why is it true? Because y is true because that is equal to x naught hat along. Okay, so y is true. So okay, so if you take any so just take a copy of this one. Okay, so take any so okay, so take any a comma, okay, yeah, because you know that this h restricted on d of a of anything, right, which is the same as h, is equal to x naught, right? So this is the same as x naught, and then you take the gamma restricted on u. Okay, so then you get x naught hat. Okay, this is our close to. Then what's next? Okay, and therefore must be equal to h naught hat on b. Okay, therefore must be equal to h naught hat on b. Okay, so y is equal to h naught hat on b because okay, so what is h naught hat? What is okay, so what is h naught hat? So okay, h naught hat is okay, h naught hat is that. Okay, okay. Okay, I think this is by the theorem we just proved last time, right? Remember? So because this d is what? Okay, so this h naught hat is what? You get this h naught hat by lifting this h. So because for the h, you know that there is like a unique lift, right? Yeah. Wait. For the h, you know that there is a unique lift. Yeah. So for each h, you know that there is a unique lift. And then for this h naught hat, yeah. So the lift must wait. Why is this on D then? Okay, I think this is okay. Maybe let's be more careful. Let's be more careful here. So okay, so why it is going to be okay? So because okay, so I want to say is that if we take any path, right? So if we take any path, let's say because okay, so what I want to say is that because if you take any h restricted on D of any path, let's say what is the path? Let's see. So the path is given by you pick a parameter inside this gap, right? Okay, so you pick a parameter. So let's pick this to be R. Okay, and then let's take the first one to be t. Okay. Where this t is just any variable between this c minus epsilon and c plus epsilon inside this AB. Okay. So you take it to be that, and then this is the path, right? So this is the path. So then what happens? So then this give you what? Okay, let's see, this give you what? So yeah, so this is just a path in this yeah. So this is a path in this what's it called? The in X, right? Okay, with initial point with okay, what is the initial point? AX, right? Because we are saying C equal to A, right? X naught, sorry. Okay, so now what happened? So because what is okay? Because it's a path, therefore well, I want to say that there is a unique lift. Okay, let's see why it is a unique lift, because okay, let's see. Yeah, because it's a path, right? And then okay, I see. Okay, because it's a path, it's being defined over some like a closed interval or something, right? So therefore, we know that there is a unique lift, right? Okay, because we know that there's a unique lift, then H tilde is like a lift, right? Sorry, H hat is like a lift, right? So therefore, this must agree with this H naught on this D, because we showed last time over this wait. Okay, yeah. So this is a path, and then wait. Why? Okay. What I want to say? So okay, because because we know that this okay. So what I want to say is that the image of this path is lies in U, right? Because yeah. Yeah, so the image of this, the image of the entire thing is actually lies in U, right? Yeah, okay. So therefore, so since this set, since the image of this set it lies in the evaluating cover open set U, therefore, and U is evenly covered set. Therefore, we get a wait. Therefore what? So therefore, we get a unique. I want to say that we get a we got a unique lift of this one. Okay. Yeah, we got a unique lift of okay. So we get unique list of this guy, okay, to this, and then, yeah, because what? Okay. Because this H tilde T, it is also a lifty, right? Because, yeah, this H hat T is also a lifty because this is just whatever we, yeah, it is just like we define it, right? We define it to be the lift that we define as now. Okay, so therefore they're the same. Okay. Alright, so yeah, this is true for any T and R, so therefore they are equal inside this D. Okay. Yeah. So yeah, that's the proof. Oh, sorry. Okay. 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 However, the point C comma R is equal to this A comma R lies in